Welcome to our new unit, which is kinetics. And kinetics is the study of reaction rates, or basically how fast a reaction occurs, and how reaction occurs, or how a reaction occurs. And that refers to the mechanisms, which we'll discuss later in the unit, of mechanisms of reactions. So, if we take a look at here, everything in red is what we have done, or I guess pink, I don't know if it's red or pink. So we started off at the very beginning of the year with stoichiometry. Then we went over to gases, then we studied reactions, net ionic, solution stoichiometry, and redox, or oxidation reduction reactions. Then we moved on to galvanic cells, and electrolytic cells, and electrochemistry. Then we studied thermochem, which is delta H, and thermodynamic, which is delta S and delta G. And we just finished equilibrium with Kp, Kc, and then Ksp. And now we're in kinetics, this is an intro lesson about what is studied in kinetics. And then after kinetics, we're going to move on to acid-base equilibrium, electrons in atomic structure, and then last but not least, which is actually my favorite unit and the one we study the most in honors biology, honors chemistry, bonding, molecular geometry, and intermolecular forces. So that's sort of where we have been, where we are, and then obviously where we're going to end up. So, again, this is sort of a summary. You can read through this yourself, a summary of what we have learned. And now we're going to be in kinetics. And kinetics studies basically two major things. How fast does a reaction happen? And what factors affect that rate? Okay, so we're actually going to look at this one first, briefly, and then we'll spend a long time in how chemists calculate how fast a reaction occurs. So again, whoa, too fast. So kinetics again studies the rate at which a chemical process occurs, and we're going to talk in excruciating detail how rate is measured. But for now, you can think about rate as a speed, or how fast the reaction is occurring. And again, like I said, we will discuss how that's measured in excruciating detail. And then we're also going to study what factors affect the rate, and to what degree, which ones affect the rate the most. Okay? And then also, kinetics also studies the mechanism of the reaction. You can think of mechanism as like the steps that need to occur for the reaction to occur. What bonds need to be broken, what bonds need to be formed, and the order in which they happen. Okay, is the mechanism of the reaction. Which bonds need to break, which bonds need to form, and the order in which they happen is the mechanism. So those are the two main things kinetics studies. The rate, and the factors that affect the rate, and then the mechanism of the reaction, which is how the reaction occurs, or the steps in the reaction. To this point, we haven't really talked about like what is actually happening when a reaction is occurring. We just have the reactants and the products, and they have some sort of equilibrium between them, but we haven't discussed what's actually happening in the reaction to allow the bonds to break, that need to break, and the bonds to form that need to form. Okay, so the ultimate thing, or the main thing that determines how fast a reaction is going to occur is the frequency and effectiveness of collisions between the molecules reacting. However, it's important to realize that not all collisions are productive. Collisions have to have two qualities that make them productive, okay? They have to have sufficient energy, and they have to have the sufficient or correct orientation. So, just to sort of look at these two a little bit more in depth, and you should probably write some stuff next to them. Sometimes collisions aren't hard enough, or they don't have sufficient energy to make a reaction occur. And sometimes the two things, when they actually collide, they're not in the correct position for the reaction to occur. Like, they don't hit the right angle for the bond to break. Okay, so, but if you think about it this way, the more collisions that you have, the more likely they are to meet these two qualities, if you want to call them that. The more you have, the more likely they're to have sufficient energy, and the more likely they are to have a suitable orientation if you have lots and lots of collisions occurring. In this image here, just to sort of look at this sort of collision thing in images, this picture is mostly about the difference between ineffective and effective collisions. So if you see here, we're having a reaction where we have A, and it's reacting with a compound BX, and A is going to kick B out, and now B bonded to X. Now if you see in the first image here, A collides with B, and that's not an effective collision, because we don't want to bond A with B, we want to bond A with X. So this, while a collision that occurs, is not effective. It doesn't make the reaction occur. But this collision here, where A hits X, and if it hits it with enough energy, it can bond with X and then kick B out. So this is an effect of a collision, or a collision that allows a reaction to occur. Now again, the more collisions you have, the more likely you are to have an effective collision compared to all the ineffective ones. So now we're going to look at factors that affect reaction rate. There are 6 of them that we're going to look at. The physical state or phase of the reactants, whether they're a solid, liquid, or gas. The form of the reactants, whether they're crushed or chunky, and we'll see what that means in a second. The concentration of the reactants. The pressure or volume if the reactants are gases. Temperature. And the presence of a catalyst. So those are the 6 factors that we're going to look at briefly. We're going to look at number 6 in much greater detail later in this unit. So, as we said, in order to react, molecules must collide. Okay? And the quicker the reactions can collide, the faster the reaction occurs. The more effective collisions you have, the faster the reaction is going to occur. Now, if you think about this, which phase of matter do you think is going to have collisions more? And this is pretty straightforward. Gas particles are going to react much faster. Gas particles are solutions, right? They move fast. They don't have like a finite space, so they're more likely to collide to each other. Where if you think about solids have limited surfaces, right? So there's only so many places that they can collide with each other. Oftentimes the whole solid is taken up by a collision. It can't collide with something else until it is finished colliding with one thing. That being said, when you're talking about, so actually to summarize, gases react the fastest, followed by liquids and solutions. And then solids are the slowest to react. That being said, if you have a solid, okay, the thing that matters with a solid is the particle size. The smaller the particle size, or the more surface area, okay, the more quickly reactants can come into contact with each other, and making the atoms collide more often. And then as a result, that will increase the reaction rate. If you remember in AP Bio, we talked about that small things or small cells have more surface area. And that's sort of like the area that an object has to collide. So the more area that they have that can come into contact with what it needs to react to, the faster the reaction will occur. And it just so happens that things that are small have greater surface area. Okay. Second, the next factor that can affect speed of reaction is concentration. And concentration, we're talking about molarity, moles per liter. So the higher the concentration, okay, the more atoms or molecules you have in say the beaker, right? Which means the atoms can collide more often. So if we take a look at this image down here, so let's say we have the green particles are hydrochloric acid, and they're going to react with a metal. Gases react with metals. Acids react with metals, and let's say this is magnesium. Okay, if we see here, assuming that the volume of these 2 boxes is the same, the more acid moles you have in the container, the more likely you're going to have collisions. So like if you're saying that the green particles are acid, there's obviously a greater concentration of acid in here because there's more molecules in the same amount of space, and therefore when there are more molecules, you're more likely to have collisions, and those collisions are more likely to be effective collisions. And again, the more collisions you have, the faster the reaction rate. So this next factor that affects reaction rate is unique to gases. Okay, so let's say you have a collection of gases in a container and they're going to react. Okay, and let's say you reduce the volume of the gas. So in this picture, that's what we're doing. We have these gases here, and then we're reducing the volume of the gas by moving this piston down, and that is going to increase the pressure. Okay, now if you think about these molecules are now closer together, and there's also less space for them to move, right? So as a result, okay, the atoms will collide more, and that will cause an increase in reaction rate if the volume they occupy is less. Because again, they're closer to each other, and they're more likely to hit each other when they're closer to each other. But again, this is unique to gases here, so it's not true for solids and liquids. But the less the volume the gas is in, and the greater the pressure, the more likely the atoms are to collide because they have less space to move, and therefore that will increase the reaction rate. So the 2 other factors that we have that affect reaction rate, one is temperature. And in AP Bio, we talked about this extensively, how temperature affects reaction rate when we were talking about enzymes. And so at high temperatures, reactant molecules have more kinetic energy. Therefore, they move faster. And if they move faster, they collide more. And they also collide with greater energy. So therefore, you're more likely to have more collisions and also more effective collisions because the molecules themselves have greater energy. Okay. Now, one thing that is true is that in AP Bio, we had enzymes, and enzymes are really temperature sensitive. If you get above a certain temperature, they denature. That's not something you're really going to be dealing with in chemistry. So pretty much for almost in all cases, the higher the temperature, the faster the reaction is going to occur. There's sort of not a point where like the reactants denature, unless you're talking about biological molecules, which in most cases, in this case, we're not. So again, that's that relationship that we learned about in biology is not the same, because we don't have proteins that are denaturing here or losing their intermolecular forces. So in general, in chemistry, I mean, in biochem, we need to know that, but in chemistry, the higher the temperature, the faster the molecules react. There's not some like maximum temperature where the rate will start to decrease because of denaturization. And this last thing, which we're going to spend a larger time talking about at the end of this unit, is the presence of a catalyst. So a catalyst is any substance that speeds up reactions. And they speed up reactions by changing the mechanism or how the reaction occurs. So everyone in this class learned about enzymes, even people who didn't have me for AP Bio. And enzymes, if you remember what they do is they bring the substrates together in the active site and allow them to collide or be in the right position to collide. That's changing the mechanism or sort of the steps in the reaction. So they choose the steps that allow the reaction to occur the most quickly. The catalyst. Now, there are non-biological catalysts that we're going to study that work a little bit different than enzymes. We won't be studying enzymes in this course, but there are chemical catalysts that have different ways of speeding up reactions and having an active site. And we're going to take a look at those. So the other thing that catalysts do is they provide an alternative pathway that's faster than the one without the catalyst. And then also, just like enzymes, catalysts are not consumed during the course of the reaction. They can be reused, just like enzymes. So that's sort of the end of this lesson, and there are guided questions to answer. Whenever we have class next, depending upon whether there's a delay or not, because I'm filming this or recording this on Wednesday night, will depend upon sort of when we learn the next lesson. And the next lesson is how do chemists measure the rates of reaction? So what tools do chemists use to measure rates of reaction? What math is used to measure rates of reaction? How are rates of reaction measured? And that's sort of what we're going to be looking at next in this unit. All right, go answer the guided questions. Have a good night.